Yo, it's Arrow, man of all things audio, and I made a VST audio plugin. We're going to do a code walkthrough of it today, but if you haven't seen this thing before, don't know what it does, don't know what it sounds like, you're definitely going to want to check out this video that's going to be linked on your screen right about now. There's going to be no audio examples in this video, so you're definitely going to want to listen to that one. This is completely technical, so why am I doing this if it's just technical? Well, if you happen to be a musician like myself, it's really cool just to know what's going on under the hood of these things that you're pressing and turning all the time. And you'll get some very basic DSP concepts of how your computer works with audio. If you happen to already be a programmer and interested in making a plugin using JUCE or just an audio plugin in general, this will hopefully be a helpful reference for you and how everything should be structured and potentially some things to avoid or some things to invest in setting up. This video is also going to help myself out because I tend to forget things a lot, and it's very likely I'll take a break from making new plugins for a while and then come back to it. So it'll be awesome to have a little video of myself explaining things to myself in my own words as a reference. So future self, you're welcome. But first, before we get into the tutorial, or walkthrough I should say, I should thank the awesome people that already tried out the plugin and gave me some really great feedback. So there's some things I'm going to be implementing soon. Really some great suggestions on the UI, some great suggestions on new features, and small changes to some of the sliders. I can do that, and I'm glad to do it very soon. But this version we're walking through right now is the old version. There's nothing added to it. This way I don't have to worry about debugging things in the middle of this walkthrough. And we still get to learn all the things I want to talk about. So we're going to be explaining the concepts of what this thing is actually doing under the hood. We're going to walk through a prototype, actually prototypes. Well, one prototype I made in Reaper, which is a really great example of how you can use JS plugins to prototype your idea, and it's actually bare bones. So we don't have to walk through all of the UI stuff that's plugging all of these extra pages over here. After we understand the prototype, then we'll look at what's actually programmed here in JUCE. We'll do the algorithm on that's on the plugin processor, and then we'll talk about the UI stuff and how that's connected to the back end of it per se. And then, as an awesome bonus, we're going to get a little bit practical, and we're going to implement a new feature on this plugin together. It's going to be the most, probably the simplest thing you can do in DSP. We're just going to add a clipper at the end. So we get a little bit of practical example of how we would add more features to this, just to see not just a walkthrough, but actually building a little tiny window inside of our structure. And a hard clipper is about the simplest thing you can program, so it'll give us just our feet wet for the people that are curious to give it a try, to see how simple it can be once things are structured properly. So why don't we get started? Alright, I find it best to explain things as if we know very little about the way audio is handled in our computers. So this is a waveform. Sound is waveforms. They wouldn't necessarily be so symmetrical or so ugly. Sorry, it's not perfectly drawn in real life, but they are definitely continuous. These lines that don't have discrete points, they just keep moving in squiggly fashion. But computers do not do continuous. Instead, we just take a bunch of discrete information, which just means we're going to take points. As we hear our audio or receive our audio, we're just going to take snapshots of where the waveform is at different points in time. If we have enough points in time, we can do some mathematical voodoo and interpolate a full waveform for our playback system to play back. The rate at which we take these samples is what we refer to as the sample rate. So if I have a sample rate of 44,100 Hertz, which is likely what you have inside of your DAW or on your audio interface or what have you, this is the standard sample rate, which is enough to represent all of the frequencies across the audible spectrum. If we have a 44,100 sample rate, that means that I'm going to be taking 44,100 samples of our waveforms every single second to help represent it in a digital fashion. If we have a slower sample rate, all that means is that we're going to lose the ability to represent high frequency information. And as an example of that, let's say instead of the waveform being very cleanly sinusoidal. We have some high frequency information, right? This very short wavelength information right here. If my sample rate only takes a sample here, and then one here, and then one right here, and then one right here, when it interpolates the waveform, it's not going to turn to a square wave or anything. It's still going to make it into a waveform, but it just doesn't represent all of this short wavelength here because it doesn't have any information about it. It didn't take snapshots at that time. So we lose, or rather it's disturbed, that high frequency information will be reflected across the spectrum. That's aliasing. It's not important. That concept is just our sample rate determines how many samples we take for every second, and everything that we're going to represent and talk about in audio going forward is just a gigantic list of discrete samples. With that out of the way, this is a line. This is ideally what happens when audio, or the signal, these samples go through your audio workstation or through any digital device. There's some sample that's input on the x-axis, and then it's returned with the same value on the y-axis. If we instead add something like a gain slider, which is what we refer to as a linear transformation, you'll see why, and I have this little gain slider. If I change the gain, all that means is that the sample is going to come in on the x-axis, and then it's going to be returned somewhere on this y-axis depending on where it is on the line. So I can change the gain to a smaller value, so now the output's lower, or a higher value, but this always remains a line. Hence, it is what we refer to as a linear transformation. On the other hand, we have nonlinear transformations. And as you can see, and let me turn up the drive here, this is definitely not a line. This is a saturation curve. This is one of the saturation curves available inside my plugin DUS. Anyone that's used like Ableton or Trash or most distortion plugins, you've seen a curve like this, some sort of sigmoid type of function, and it's actually that simple. What it's doing isn't some wonkiness. It's not, if it's not analog, if it's not some sort of analog emulation. If it was, that's a completely different thing. There'd be transfer functions. I'd be showing you this in MATLAB, not Desmos. But for our digital saturation types, and what I'm doing inside of the plugin is actually just these very simple curves. They're guesstimations, if you will, or some very gross simplifications of some of the nonlinearities inside of an analog saturation. But what's going on is the same thing as what's going on in that line. A sample comes in on the x-axis here, and then it's returned somewhere on this curve, depending on how high that value is. So we get a gigantic list of samples. All of them pew, 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 are mapped to this curve, and in the end, we have a saturated signal. This adds harmonics, which is why I care a little bit about the sample rate. For now, that's not an important discussion. All we need to know, is I'm going to remove this gain slider, is what my plugin's doing with dynamics is it's taking this linear line and it's slowly morphing it into, it's actually rather quickly morphing it into this distorted signal. And somebody that's a little bit more familiar with distortion might say, is like, well, isn't that exactly the same as just moving the drive knob here? And it is actually quite different, believe it or not. But both things are modeled, or you can do both functions inside of the plugin. Just an easy way to visualize it so you can see is that this waveform, when I'm changing the drive here of my saturation, it's bending mostly from the middle as it goes up. And as I change my interpolation between the linear line and this saturated curve, it's actually bending from closer to the origin. Exactly why this sounds so different? Well, number one, we have to recognize that this -1 to 1 is the entire universe of what's actually going to be played back. So this is actually a very large difference in shape. But the important part, this is an audio thing, is it does actually sound different. And to clarify that, so you can hear it, especially you can go back to the demo and hear it. But when I have the dynamics on and distort is on, what it's doing is it is changing this drive knob. So that's like changing this K value here and changing the drive on my distortion. If instead I have my dynamics on but distort is off, then it's like this yellow line that's just mapping to the curve. And it's going to sound way more gentle and less aggressive than the drive knob. but still make a notable difference. With that out of the way, we have to consider how we're going to get from this line to the next line. What is making it change? And that is where we're taking values from our samples and trying to find the average level of the signal. And the typical way to do that with a sinusoidal function or with some sort of current is what we refer to as RMS. And let me get a bolder color here. Bolder line, I should say. So RMS stands for root mean squared. And what that means is I'm going to take some bag of samples here. It's a rather large bag, but what I'm going to do is I'm going to square each of these values. Everything squared. I'm going to find the average of those values. So let me draw it like this, right? I take all of these values, put them together. I find the average of them. Here's our mean. And then I find the square root of that. I believe this is geometric mean. Somebody correct me if I'm mistaken. But this is how RMS is taken. What doesn't work about this nicely, if we don't think about the problem a bit, is that how many samples am I going to be taking if my windows, and this is the range of windows I currently have, I have no idea why I let it go all the way to 1000 milliseconds, but let's just say it goes up to 600 milliseconds. But let's just look again at the smallest value. How many samples is there for a 60 millisecond window? Well, if my sample rate, again, we're going back to our foundations, I guess. If we have our 44,100 sample rate, that means for every second I'm taking this many samples. How many samples is it for 1 millisecond? Well, I'm taking 44, right? And then if I multiply that by 60, I'm getting some, let's say roughly 2,500 samples here. If I have 2,500 samples here, and I do this problem very, I don't even have a word for it, very brute forcely, we'll say, then that means I'm doing 2,500. I'm squaring 2,500 values. That's 2,500 functions. And then I find the average of that. And then I find the square root of that. Well, if we think about the problem a bit more, we can avoid doing like 2,500 plus actions for every single window, every single millisecond, every single sample rather, because every time a sample is added to this window, then we have to do the function again to know what the current RMS is. What we can do instead, let me just clear all of it, is if I have a window, let's make it a not so big window. Let's say I have a window of like 5 here, right? What I can do, if I recognize what the problem is I realize every time the window slides for every single sample that's getting added here, I'm really just taking one sample away from my big sum here, and I'm adding one sample in. And I can avoid squaring all of these values because I realize every single value here should already be squared. So why don't we just square the value as it's plopped into our basket here? So what I'm going to do is I'm going to have my big sum, and this is going to help us as we walk through the code so we understand like all the lines that I've written, what they're actually representing, why there's some extra variables that don't seem necessary to do like 3 functions of squaring and then mean and then root. So at every step, I'm just going to need to know what my general sum is. I'm going to subtract the last value, and then I add this new value here. And then I can take the average of that and find the square root. And now I'm doing 4 steps instead of 2,500 actions per every single sample that's added here. That seems to solve the problem, but we also have to consider, this one's more for the music producer that already knows the waveform stuff, the stuff like sample rate and what saturation is. This is more for the coding half if you're not familiar with this. If I have this window, it's a list or a vector or an array or whatever. So each of these has an index inside of my list here. I can't just always put this into index 0 and replace this last one, this index 0. Otherwise, these never change. It's like my window is never sliding. These should be eventually getting out of my window after 5 steps, 5 samples. Instead, these are just going to persist forever, and I'm only going to change one value. So how do I keep track of where I am in this list, which one to replace? Well, we have this thing called, this is where the modulus division is going to come in handy. I need to know the size of my list, and that's really important because I'm allowing you to dynamically size this list, how big the window is, right? It could be 60 milliseconds to, I'm probably going to change it to 600 milliseconds. So if I know how big the window is, every time it gets to 60, if I do 60 modulus, let's say 61, or the other way around, if I do that, then I'm going to have the remainder 1 at the end, because I do 60 modulus 60, divide by 60, that's 1, and then the remainder is 1, so I end up right here. And then if I do 62, the remainder is 2, and then the remainder is 3, and then 4, and so on and so forth. So that will help me navigate through this window, and as long as I keep track of what the window size value is as well, I can dynamically size this window and make it so that maybe there's 50 samples in here, right? And all I have to do now, there's another thing we have to consider, is that we always have to be checking to make sure that this window is filled. So if I go from 60 milliseconds to 600 milliseconds and I don't remind myself, hey, we need to have a full list before we care about doing this modulus division, we need to actually have samples in remainder like 72 and remainder 100. As long as I keep track of that, we have all the variables we need, all the values saved that we need to help navigate our way through this window, add the values that need to be added and subtract the one that needs to be subtracted, and get our RMS value with this moving window. Hopefully that all made sense. But even if it didn't, we're going to walk through the code, probably not as much in this detail, and help this make a little bit more sense and put them into action. So why don't we step over, not to JUCE for the actual code, we're going to step first into the prototype and see how we can do this with a pretty basic language EEL2, which is made specifically for doing little plugins like this in Reaper. See you there. All right, before we get to the prototype, there's one more concept I do need to explain that's actually extremely important. It's one of my functions here or one of my parameters here inside the plugin. I did mention this curve knob, and we're gonna demystify it a bit. So what the curve knob does is it changes how it interpolates between the two values, right? So if I'm sliding between the linear line and my distortion curve, I need to know if I'm going to jump there, if I'm going to move there smoothly as the RMS changes, or am I going to resist changing and only move when the RMS is extremely high, very close to the threshold, or do I move anywhere, anytime that's even vaguely close to the threshold, I start moving up. That is what's going to change how it interpolates, and that's what the curve knob is for. So this is a simple interpolation between 2 points. Don't worry about what the actual functions are here. Basically, the idea is that I need something that will get me from 0. Let's say that my drive is at 0, and the range knob for the drive is at 5, let's say. So I'm going to go from 0 to 5, right? If I do it in a linear fashion, this is linear interpolation, I'm going to go from 0 to 5, and it's a straight line. But I like to have different forms of curves. I don't want it to always have a linear response to the change in RMS value. What I want to be able to do instead is maybe it's an exponential curve where it resists changing, or maybe it's something that looks a little bit logarithmic, that even if it's vaguely close, if the RMS is vaguely close to my threshold, I want it to be pretty close to fully saturated. That's what this curve knob is going to do, and that's what this function's for, right? So this one was actually quite fun to put in. What I have here written out in one line, and you'll see in the code I put it into 2 lines to make it makes more sense to me, and I can change it more. But this one function, some of you may recognize, it's a Bezier curve. And what you can do with a Bezier curve is it's really like it's like a double interpolation. There's no point into getting exactly how that works. What we do need to know is that changing this t value is going to change the curve, right? So I can go from this exponential looking function right here, where it resists and then changes very quickly towards the end, and I can go into this seemingly vaguely close to a logarithmic function, like so, where it jumps very quickly to the high value and only slowly moves to the top once it's near the threshold of whatever my b is, right? And as you notice, there's kind of a problem. There's a little bit of a problem here, right? How do I know what the t value should be, right? If the t value is like this, then my value is gonna overshoot. It's gonna go higher than what you set the maximum drive to be. Or if I do something like this, now it's gonna go lower than what what your minimum value was, and that's kind of a problem. And you might think, okay, well, if I just put it at 0, that works. Only if we're modulating from 0 to 1. But again, my sliders, so again, my sliders, this one can go from 0 to 10. This one can go from 0, I think, to 5. I can't remember what I set it to, or 0 to 10. But let's say they both go from 0 to 10. What happens if A, the minimum value, my minimum drive is 1, and then my maximum drive is 9, right? Now putting T at 0, and you can barely see it, but it still happens. Let's do something more dramatic. Let's say I'm at 3 and 9, right? Now all of a sudden it's going way below your minimum. Before it does nicely land exactly as we want when we're at 1 at the end of this intermittent value. Once we get to 1, it is exactly at 9. It's getting there where we want it to be, but there's this weird shape to it. It's not responding the way you want it to at all. And what this ended up being is a little game I played of, okay, let's set it, and then I would write, okay, at 1.4 it works between these numbers, and then at 1 and 8, 6, it works at these numbers. And I played this little game for a bit, wrote down the numbers, and then what we have actually, we have 3 variables here, and we have a system of equations, like a very solvable system of equations. I can't remember what I feel like I should have just put this up before I looked it up before I made this part of the video, but we're gonna see it in the code what the actual function is. It's pretty simple in calculating exactly what the t range is, but that's another variable we're gonna see in the code that I need to explain. And we're also going to see the function for the Bezier curve. I just wrote it as a little method. It's not going to be this one line thing because I really like having it make sense to me and being able to change how the curve actually works. I have done that before and it's kind of handy. But without any more further ado, we're finally going to go into the code and see how this is going to work. All right, here we are in Reaper, and I'm going to show you how to make a JSFX real quick. We're going to use an example one, actually seeing how it works, and then we're going to go into my actual prototype. So to make a JSFX plugin is actually very simple. You pull up your effects window, you right click in this area over here, and it's prompts you for the file name and the description. It's important to know the description is what you're actually going to be searching here, and the file name is literally just the file directly. So I can call it something, and I already named one stupid, but it's going to be a different file. I think I named a file something as well, so we're going to have to overwrite that file, right? So if I wanted to look for this plugin, I would go to my FX, and then I would search up stupid, but I already have one with that same name. What it gives you by default to see the code is in this edit button here, and it gives you by default just this gain slider, and the gain slider does exactly what you expect it to do. So let's go ahead and test that out. We have this random drum loop I have from Splice. Clap your hands. All right, so the gain knob is going to do exactly what you expect it to. It makes it quieter, or it makes it louder, and that's all there is to it, which gives you an awesome outline on how to make a JSFX plugin too. So starting from the top to the bottom, and then maybe a little bit to the right, we have our description, which is just the name of the plugin that you'd be searching up. The sliders are the sliders you see here, and adding a slider is actually this simple. I can add slider 2, and this part right here actually isn't necessary, but I want to make a variable. Let's say I'm going to call this variable orange. This is my initial value. As you see, it's by default 0 from this one. This is my lowest value, and this is my highest value, and then this is my increment. So if I want to change it so that this slider just adds 0.1 gain or 0.11 gain every time, then I can do it like so. And I can name the text or just change the text to the side here, and I'm gonna call it some stuff, right? So another reason I just love prototyping in JSFX is I can just press save and now it's there, like boom. So I have this extra slider, and now you'll notice it has these very odd increments because it's incrementing by 0.11, and it goes from negative 150 to 12. And it's important also to know this isn't necessary. It's only if I want to create a variable. Speaking of variables, this little, I'd be very generous to call it an IDE, but this editor, code editor here, actually saves your variables, and you can see them in real time change, which is awesome. So I can see this new variable I created, orange. This is its current value, which is 12, and as I change it, you can see it change here. So with the slider part out of the way, and let's go ahead and keep going down the code here. These in pins and out pins are going to be familiar to Reaper users or producers in general. This is how many inputs you have, input signals you have, and how many output channels you have. So in Reaper, it's this part right here. If you know what this is, you know. If you don't worry about it. But let's say I wanted to do a sidechain, I can add more inputs here, and I can call it sidechain 1, and I can call this sidechain 2. Right? I press Control S, and boom, it has been changed, and I can see I have some more extra sidechain inputs. If you don't know what that's for, don't worry about it. It's not important for today. As we slide down, we have these tags, and these tags are for different sections of the code that run at different times. The init section happens every time that you add this plugin to a track. This automatically runs and sets your variables to whatever value they need to be. Just so you're not spooked out by this function, this is the function that changes a decibel value to a sample value, because our sample values only go from -1 to 1. They're normalized, but decibels go from like -100 whatever to 0. So this is just the function that changes how much gain you slide here into a sample value that it needs to multiply by. This slider section here only runs when a slider is moved, and it runs when any of the sliders are changed. So if I make a variable, I'm going to call this variable pickle. I don't know why I'm doing like veggies and fruit today, but I'm going to call it pickle, and I'm going to say that pickle equals 0. Actually, since I just want to initialize the value, why don't I put this over here in the init section? And you're also going to see this variable appear to the side here when I press save. Boom. My pickle here exists, and this is its value. Now let's watch its value change when I change the slider. So I can say pickle plus equals 1 in the slider section. I press Control Save, and pickle's value isn't going to change because this part of the code only runs when I move a slider. If I hold a slider, it's not going to change. But when I click it, you notice it go up to 1. And as I slide it, the value of pickle is going to keep going up and up and up and up and up over here. And that happens when I change any of the sliders. If I stop sliding, it stops moving. It's only moving when I slide. And the exact frequency of that is not important for today and won't really make any difference, but that's how that works. And then the next part of our code, the next tag here, is the block code. The block code happens every block of samples, right? So it's better that we don't necessarily work with every single sample that crosses into the plugin, except in the sample block. That happens on every single sample, but the block tag only happens every 512 samples, and you can know that because the sample's block value is 512. I believe I can change that. I've never done that. There's no reason to, but that's how many samples it takes, how often this runs, every 512 samples. What this function is doing, just so you know, it's, let's say next gain. Next gain is your goal gain, right? Next gain is the value set by the slider, gain dB, right? So this gain dB value is whatever the slider is at, and next gain is that value, just turned into a sample value that goes from -1 to 1. It's normalized. And next gain is going to be, it's going to find the difference between the goal gain and what your current gain is at, essentially. And then it's going to divide that by the samples block so that it smoothly transitions over this distance, right? So last gain is, again, this is what's going to be added. It's going to add dgain, which is this function, which is based off of the distance between the goal gain and your current gain. So this is what is commonly referred to as gain smoothing. Again, it's not important for our plugin. We're just trying to understand how this works, and I don't like having like mysterious code on my screen. So that's what it's doing. And this final tag here, I already mentioned, this is the samples block, and it happens for every single sample that the plugin comes across. And what is this mysterious variable, sample SPL0? And I already spoiled it. What is SPL0 and SPL1? It's never been declared. Where do these variables come from? These are automatically just part of the plugin, part of EL2, I suppose. And these sample values are, the SPL0 and SPL1 are your sample values. And they actually are representing channel 0 and channel 1, or for most people, you think of it as channel 1 and channel 2. So left, everything you hear in your left speaker is sample 0, and sample 1 is every sample that's coming on in the right speaker, or rather the output, because I can change these if I wanted to swap them. So let's see what happens if I comment this out. It's kind of like Java. It's the double lines here. And now when I slide the gain knob, you're going to notice the left channel change. I'm assuming you guys are listening in headphones or have monitors or whatever. If not, it's just going to sound slightly softer. But you're going to notice that the left channel is going to change, but the right channel is not going to anymore. Right? So the right channel is staying loud, the left channel is going down to negative 77 decibels because I'm no longer changing sample 1. I think I got it backwards. Are my headphones on backwards? Okay. so yes. No, that's right. So sample 0 is your left channel, sample 1 is your right channel. And you'll notice times equal, that means that it's multiplying it by the gain value. Just like we saw in the Desmos calculator, we're just multiplying it by some value, and that changes the slope of our line. It's a linear transformation that's going to give us some different output based on what our input is in that slope, the slope of that line. So that's generally how this works. Don't forget your semicolons. And with that information, that's enough to understand what's generally going in the format of EEL2, as it's called, or JSONic. But for the coding people out there, I want to show you something really trippy. So this isn't, we do have arrays in EEL2, but it's not, we have an array, I should say. We don't have arrays, but we have an array. So I'm going to initialize a value. I'm going to say that pair equals 0. And I'm going to say that apple equals 5. Right? Makes sense so far. I'm going to say that apple at 0 equals 10. And you're going to notice, usually you have an error, it's going to tell you right here, but it tells us we recompiled, okay, so this, whatever I just did is all right. It is now, I'm now telling it that apple is a place in our singular array that we have for this entire code, this entire plugin. So this is, apple at 0 is 1 in this list. And if I want to add more to that, let's see what happens if I access this value, but from pair, because pair is also a list. It is also the same list, this is going to be a little bit weird. So if I say apple zoo equals pair at 5, let's see what we get. So here's zoo, and it has the value 10. Because pair is the same list as apple, and apple is at location 5, and location 5 of pair is whatever I set apple at 0 to be, which is 10. I just find this entertaining. So that's a trippy thing about the language for anyone curious to have a whack at it. There's one more thing I should cover before we look at my prototype. There's also a GFX section, and this is where if we want to have a little interface at the bottom, which I do, we add stuff to. So it's a tag just like any other, and it has some variables that automatically exist. Like you'll see the GFX R, G, and B here. But that should be enough for us to understand what I'm going to show you in the prototype. Let's go ahead and move on to that. All right, so we have the plugin here, but before we get into details and open it up, it's important to know two things. Number one, this is going to be it's going to be a lot, and it's going to be pretty messy because nobody was actually ever supposed to look at the code for the prototype, but I felt it was something pretty cool to share. Just know you can look at the chapters below on YouTube and skip ahead to if you're only interested in seeing how it's implemented in JUCE or in C++. But before you go, there's one more concept I forgot to explain, because there's going to be a variable flying around that you're not going to understand otherwise, and I've tried recording this part a couple times. So we have the threshold, right? If my RMS values, which can look like anything, it's not going to look like a waveform, right? It's not going to look quite that ugly, right? But we're going to have our threshold, which might be here, right? And our RMS value hits it, maybe it goes down, maybe it goes up. And if I'm in direct mode, if it hits this threshold, anything above is going to be at the maximum amount of saturation. But my question to think about is, what about if I put an inverse? In inverse mode, I say the lower the RMS value is, the more saturated it is. But what's the bottom floor? So the noise floor, at least occurring to this, is negative 319 decibels. So let's just put negative 300 dB down here. If I'm measuring a signal that's dynamic, that's actually playing through, the RMS value is never going to be negative 300 dB. So this is never going to be fully saturated. So what do I do to make sure that the inverse part works the way you want it to, that at the lowest value it's as saturated as possible? What I do is I have this variable that's moving with a window. Again, we have more moving windows and more interpolation here, I'm sorry. But let's say that my signal is generally around here, like maybe negative 100. It really doesn't matter, right? So the local minimum right here would be my low. I call the variable low, or RMS low. That's just putting it from the sample world of -1 to 1, and it's putting into the logarithmic world. So this is the decibel value. So this is the lowest value in the signal, lowest RMS value I have in my signal in this window, right? And then the window keeps moving on, and I find whatever the lowest value is, and I keep changing what the RMS low is. And that way, if I don't have to worry about the signal being low here for a while, and then the lowest point over here is over here, right? We can't just save one low and assume that it works for the whole signal. It's a moving window, and after so many samples, I forgot exactly what I chose, but it sounds nice, so we're sticking with it. Every once in a while, it'll change and update. So if I find a new local minimum, it'll automatically change. Okay, RMS low is here. And if I go through, I think it's so many, let's say it's 100 samples. If I go through 100 samples and I don't find a lower value than that, then whatever the lowest value, whatever this value is here, is now the lowest, right? So now this is my low. And if I find a value lower than that, it keeps moving, right? And it never stays the same for more than 100 milliseconds. So I don't remember exactly what the interval was, but it never stays the same for too long, so that it's always finding whatever the lowest possible lowest RMS value is in the signal for any given window, so that I know which value should be the most saturated, and I can find a ratio between that and the threshold as I move along. So hopefully that made sense. But so we don't, again, I hate having a bunch of like statements in code that we just don't know what it does. Let's go ahead and open it up, where we will see some real chaos. So here's the code. I find it best to describe it from the bottom up. We have our GFX section right here. These two values are basically telling the system how big the window should be. I have it 192 by 192. I saved this variable GFX size, but I already know there's no reason to use it. It's for me to use in the future if I wanted to draw a line that's like halfway through or a third of the way through. Having the GFX size saved as a variable helps me do like ratios for that. But there's no reason to, since I'm not trying to draw anything across my window. These two functions, changing hue to RGB and GFX HSL, this is letting me change the hue, saturation, and light by the RGB values and like going back and forth between them. I apologize because I forgot exactly who I grabbed it from, but you can find it. You can probably Google it on the Reaper forums, how to change RGB values to HSL values. The reason I want to use HSL values, the hue, saturation, and light, is because I have this little indicator here. All the stuff that's printing out, it's really just for debugging. It's not actually part of the plugin, but it's super handy. What you're going to notice, I'm going to turn it on. And what you're going to notice is that this thing's going to light up off and on. And that's letting me know when it's super saturated, it's going to be really bright. When it's not saturated at all, it's really dark. And that's just an indicator I use to make sure that the plugin's working the way it should. And all this code, again, like this part was just copy pasted for functions. This is actually a good opportunity to let you know commas actually aren't necessary in EL2. It's kind of weird, right? It's still gonna work. So you're gonna see a couple of functions spread out across here. I put it in the GFX section and then one at the init section, so I don't have to look at the functions everywhere. but this part is just copy pasted. This is the format of a function. We have our parameters at the top. I may or may not use commas. It actually just doesn't make a difference. And instead of having braces, we have the parentheses and then the semicolon at the end. Cool. So these statements are me setting the RGB values. So they're GFXR, GFXG, GFXB, and then the alpha value is GFXA. I have GFX X and Y, and those values tell me where I'm going to start drawing from. So at GFX X is 0 and Y equals 0 is this like top left corner. And then I draw this rect to the width and the height of it over here, right? So I feel like that's self-explanatory enough. I change them all to 0 so that it would be black. And that's me. This is me, all just me drawing the square here. Then I just change it to these values, and they're just literally kind of made up. I just did that so it's a different color here, and it happens to be this reddish, orangish kind of color. I said GFX X and Y again to the top left corner to right, and then I write the whatever the current log RMS value is. And again, this little function changes it from sample value world to decibel value world, because again, samples are normalized from -1 to 1, but decibel values go from like negative whatever to 0. And then again, RMS low, RMS threshold. This is just me checking that the values are as expected. And as I change the threshold, you'll see the threshold value change here, right? And it's also, oh wait, I changed the intensity, but yeah, cool. And this will also change the K value. We'll talk a little bit more about how these things are correlated. I kind of already explained it, but we'll get back to that another time. So after after I set those values, I have to actually write them on the screen. This is the function to draw in GFX in this language, and it's kind of weird. This is one of the things you just like copy paste from the documentation and then fill in the variables where you need. And then I change the Y. I don't know why I keep setting GFX X again. It stays 0, but I changed the Y, so now I'm a little bit lower. And then I write again, and then I'm a little bit lower. Y equals 20 or 30, and then I write again. And now J again. I have to apologize. Nobody was supposed to look behind the curtain here, so there's gonna be some really stupid variable names. But J is just for like the juice amount. And another thing you need to know about this language at EL2 is that there are if-else statements, but there aren't if-else statements. There are conditionals, but there are no if-else statements. So everything looks like a ternary operator here. I'm trying to set the value of J, right? So J equals, well, if correlation is true, then it equals this. It is the threshold versus the current RMS. It's this ratio. So when RMS is really close to the threshold, it's basically full, and when RMS is really far from the threshold, it's a lot smaller, then it's going to be 0. And then else, this is, okay, if it's true, it does this, else, we have the colon, it is ratio. And ratio is something that's calculated, again, from the RMS low amount and something else. Here's another if-else statement. So if correlation is true, then I'm going to set it so that it's bright and highly saturated here whenever the saturation is high. And I'm going to set it the HSL the other way around if it's indirect, right? So if I have it so that our, what was I? Okay, so dynamic, I'm so mad at myself. Things are terribly named. But correlation is this dynamic thing here, this window. So if I'm indirect, then the correlation is, the higher it is, the closer it is to the threshold, the more saturated. If I'm in inverse, then the farther away from the threshold it is, the more saturated it is. Sorry, again, it's kind of nasty how I name things, but we have this just to let me know, okay, is JUCE working at all or not? And when I switch to inverse to direct, you'll notice JUCE isn't working at all because it's not anywhere near the threshold. So lastly, I print the K value at the bottom right here. So, and that's it for the GFX section. Now we're gonna start walking our way up and explain things from the bottom up, I suppose. It's gonna make the most sense. This was me attempting to do mid-side, and it just did not work out. So this mid side question mark, right? This variable name comes from the slider where I named the slider mid side. So if this mid side drop down list is on off, then it won't do anything. But if it is true, if mid side is true, then it will do this. And pi, just to let you know, if you see anything that's a vegetable or a dessert or a fruit, if it's edible, then it's a debugging line. This is just to make sure that things were working as intended. We can ignore the fruit. So again, this part didn't work out, so don't even worry about it. Last gain plus equals d gain. This is actually from the boilerplate code. I don't even remember if I fully implemented the input gain knob here, but it's there. Some of the lines of code are still hanging around. This is I called this plugin JUCE before, so this is the actual distortion unit. So I had three like equations, three sigmoid-esque functions that you can choose between. So if you choose slider 3, again, this is what happens. This is how you call it if you don't name. Oh dear. 1, 2, 3, 4. Did I? Did I misname the sliders? Oh. Okay, cool. I just noticed something that I changed. When I changed slider 3, I forgot to change the slider it's going through. Okay, so we can fix that right now. You notice that when I changed the clip type or the distortion type, it didn't change sound. That's because all of these should equal 4. So if slider 4 equals 0 or slider 4 equals 1, right? And I don't have to specify here because if it's not 0 and it's not 1, then it must be 2, right? So sample 0 equals this, sample 1 equals this. Remember, sample 0 is just the left channel, sample 1 is the right channel. And this is the if-else statement. So if slider 4 equals 0, and remember, there's no if-else, this is the only way we can write conditionals. Else, if it's true, do this. Else, if it's 1, do this. And if it's not either of those, then do this. You'll notice K is the distortion value, just like we used in the Desmos calculator. And again, these are just like copy-paste functions I've used for distortion. This is pi, if you're wondering what the random number is. And this is, I forgot, I think it's just specifically 2.12. Somebody can remind me. Is that some, I feel like I should know what that is. EXP is exponent. For a while I thought it was like use like the power function where this is the root and then you multiply it to the power of the second value. But exponent is actually e to the power of whatever you write here. So just so we know what all of these functions are. Atan is arctan, as you could probably guess for yourself. Yeah. We have our little functions here, and that'll just change the sample values. If we go up a little bit before, we have the pre-distortion. So this is the boost function here, and I actually didn't implement this in the final version. What this is doing is it's actually doing a different distortion type, and it actually just sounds nice, almost like you can think of it as like a preamp kind of thing, where it runs through this first, and then this change sample, new sample 0, sample 1 is run through the other distortion. It actually sounded kind of nice. I might implement that again in the new version just so you guys can hear it, but don't worry about it. It's just another equation, copy paste function. Then we have this is the gain. So I guess the gain knob is implemented. We're multiplying it by the gain just like we saw in the boilerplate code from the JSFX sample. And this is where the juice actually happens. This is where the saturation happens. So again, correlation is, am I doing inverse or am I doing direct? Do I saturate more when I'm closer to the threshold or less when I'm close to the threshold? Right? Or inversely, do I saturate more when I'm really quiet or less when I'm really quiet? So if correlation is true, right, which means it's in inverse mode. I'm glad I reminded myself here. So if it's less than the threshold, and I have to remind us, right, if we have our threshold here and my value is over the threshold, there's no reason for me to change the value from here because I only saturate more as I get further away from the threshold. Anything over here gets the minimum amount of saturation. I hope that's clear. So let's look at what it is. This is bezier, and like I was saying, we interpolate between our curves. So depending on how close I am to the threshold, I need to decide, am I doing a linear interpolation or is this one that has that slope? Let me remind you with a quick drawing, right? So I can do this sort of interpolation, or I can do, let me just erase, or I could do this sort of interpolation between 2 points, A and B here, right? So that's what bezier is. It's a little function, like a helper function I wrote towards the top. And if you're familiar with the Bezier curves, this probably looks pretty familiar. I know, yes, I can write this as one line of code, but again, I like to edit things. These are my parameters: start, end, control, and t. So this is I think you call it an exponential Bezier curve, or it's one where you add an extra point, and this allows me to have the curves I want. We could actually add another control if we wanted, but there's no reason for it. T is just telling me how far I am on my curve, right? So if I'm really close or if I'm really far as my x values, right? So we can go between 0 and 1 always. That's just how I wrote the function. If I'm at t equals 0.5, right, depending on what my control value is, I am up here, or if my control value tells me I'm doing an exponential curve, then I'm right here. Hopefully that's enough to make sense. But these are just my helper functions I use for the interpolation. This one was garbage. We trashed it, but this was before I had the idea. It's like, why not, instead of doing a bunch of different types of interpolation, let's just do one. Let's have a solution that you can just modulate between, which was handy. And this is just linear interpolation. I hope the names make sense. Like linear interpolation is LORP, and then Bezier interpolation is bezier, because I thought it was cute. So we're interpolating between the base amount of drive and then drive plus intensity. Intensity in this plugin, again, I apologize for the terrible naming. Nobody was supposed to see this. But intensity is the range. It's like the range knob in the full completed plugin, right? So range tells me I'm going to change the drive from here to here, or whatever it might be. C is actually from this slider up here, it's the curve amount, right? So again, curve is telling me which type of interpolation am I doing. Is it the one that's kind of exponential looking? Is it linear, or with a closer to a logarithmic curve? And then this is telling me how close the ratio is, which is the distance between the threshold and the RMS value and the threshold and the lowest value. So it's, we'll draw that a little bit more in a second. But the idea is, if RMS is less than the threshold, then it's this function to tell me how saturated it is. Otherwise, this is the colon, k equals drive, because it just equals the minimum amount, because it's gone past the threshold, right? If the value's up here. It doesn't matter, because I'm in inverse mode. Otherwise, it's kind of flipped. If it's less than the threshold, then I'm going to have if it's less than the threshold, then I'm going to be at the maximum saturation here, which is why it's drive plus intensity. So that's the maximum amount. And if it's less than the threshold, I have to do some sort of interpolation to know how far is this from my lowest point in the threshold. So I have to, again, that low value is super important in giving an idea of what the range of the distortion should be based on the RMS value, if that makes sense. Cool. So low equals correlation. This was me letting me kind of simplifying the problem. If I have correlation on, then I need to keep track of the RMS low. If I don't have correlation on, I just made up a value, honestly. So I keep drawing it, right? So I just made up a value and said that this is just like the minimum, 0.01 or whatever it is, right? So this is just the minimum. And then I do interpolation between this value. It can be here to here for maximum saturation or minimum saturation, right? With the inverse on, I have to change this and keep track of where the lowest value is. I hope that's clear. Now let's talk about how I implemented keeping track of the RMS. All right, so I realized I first need to explain, to make this clear to everyone, I first need to explain what this RMS size is and the RMS increment is. So if we go back to the top where we declare our sliders, or rather where we do actions on the slider, our RMS size is this calculation. If I have a sample rate, let's say it's 1,000 for every second, right? I have to decide how big my window is. So the slider you have for RMS time in milliseconds right here is what's updating this value right here. So if I decide I need, let's say, 1,000 seconds, right? I divide that by 1,000 because right now it should be in in seconds. I divide that by 1,000, so I have the milliseconds, and then I multiply that by the sample rate. So I know how many samples I need per this RMS size window. This is the window size of the RMS. Hopefully that makes sense. RMS increment in our calculating the RMS section here is just telling me literally exactly how many samples have I seen. So before we get a little bit too far into those weeds, a square sample, remember we described our bucket. So we have our bucket with some samples. We're going to add a new sample in. It's definitely worth it to just square the sample to begin with. So I have square sample. This is the new sample I just saw. This is either it's the maximum of the left channel or the right channel. It's whichever one is higher. So it's always going to assume that the left channel and right channel are more or less the same. Right now it's doing it, again, this is, it's not stereo independent. So we add that new value, the new square value we just plopped into our bucket. We add that to our square sum, and this will help us find the average in a second. Then we have to, so overall square sum, we don't use that, letting you know, because this was me being curious about keeping track of the RMS over the entire time we're listening versus the RMS window. This was a ratio I was using before, which actually had really interesting results, but that will remain a mystery to you for now. RMS list lets me know, this is again just finding the space that I'm in my RMS list. This is the wonky one list type of thing. So depending on how many samples I've seen, and I do that modulus with the RMS size, the size of my window, to know exactly where to drop in this new sample, right? So I find my spot, RMS list at that spot has the new square sample plopped in. So RMS inc being less than RMS size means that I have this big long window, but I haven't seen enough samples to fill it yet, right? So there's just a bunch of blank space here. If there's a bunch of blank space, then the value least recent, the one that we would usually replace, is going to be set to, well, first we need to double check. If this is the exact first sample, RMS inc equals 0 means my increment, I've seen all the lists, the increment for all the samples I've seen. If I've seen 0 samples so far, this is my very first sample, then least recent is the same as it's the sample I just saw, because I've only seen one sample. That's the least recent sample. Otherwise, it's RMS list at 0, as in it's still this one. This is the least recent. This only applies, again, all of this part, this only applies if I've yet to fill my bucket. But if I have filled my bucket, then I'm going to do much the same thing. But to find the least recent value, I need to do a little bit of math, and this is where I do modulus division to see, I'm going to find where my position is, and then I use the modulus division, I use modulus division to find my position, and then I find the one behind that. And then I still have to double check with modulus division to make sure if this one is the one I just plopped in, then I might have to go back and look at the front of this list. And I can look at the front of the list all the way up here because I know it's filled. This part only happens if the bucket is full. Alrighty. So RMS, this is just a function. The 1.41421356237. This was a little bit of math I did because I was curious. I changed it back. You see it set to 2 different values here. It's set to one value, then it's set to another one. The reason I did that is because multiplying by this value, if you have I know this is super random. If you have a sine wave and you find the RMS value is something like 0.717 for a 1 decibel sine wave. And I was curious what would happen if I just set it so that multiplying by this value will turn 0.717 into 1, right? And that gave me RMS values that to me felt better. But again, I just changed it back. At least in this, I don't even remember what I did for the JUCE plugin. We're gonna find out. with that out of the way, now this is where I decide what the low value is. And we have to be keeping track. So RMS time, the floor for RMS time over 400, 500 by the sample rate, that's just the amount of time that I change for the window. So this will be the lowest point here. And if I go so far, whatever this value ends up being, if I go this many samples and I haven't found a lower value than this one, then I'm just going to call whatever value I'm seeing right here the lowest value. And this is saying if RMS is less than low, or this applies true, where I've gone through this many samples and I've seen nothing that's lower. If that happens, or the current sample I see gives us an RMS value that's lower than before, now I update what RMS low is. So RMS low equals the current RMS, and then the low counter, which is this counter for the window, it resets to 0. Otherwise, the low counter is going to go up because I haven't updated the RMS low. Hope that makes sense. And then RMS int goes up because I've seen another sample. That is the RMS section. That's going to help us find our RMS to compare to the threshold and then calculate the amount of distortion. Again, up here was me trying to think about mid-side. This is supposed to split it easily. I just did not like the results. So you can ignore this. I don't even know if I did it right because I remember I just kind of trashed it after that. This is editable, so it is debugging code. You don't have to worry about that. This is, again, part of the boilerplate gain knob. This is the stuff that happens whenever we change the slider. So K is, I changed it to K because now it looks like the actual formulas I've seen. But K equals drive. Drive is just it's the name of this knob. So it's the exact same thing. Whatever you change this to is K, is the distortion amount, or drive amount, I should say. Threshold, again, you're setting the threshold in decibel values, and I needed to convert that decibel value to a sample value from -1 to 1. I already talked about the RMS size and next gain again from the boilerplate code. This delta function is just helpful to make the comparisons. I don't even know if I actually used it. This was part of calculating the distance between the threshold and the low value, but I didn't even use it. I just wrote it to help myself in the future, I suppose. Well, I didn't know I was never going to go back to this code. It's been fun to look through this whole thing and see what I messed up. I will, again, I don't know if I probably already said this in the video, but I might as well add this to my rescript repository. You guys can download the plugin as it is. In case you're curious to play with it, see how it works, see if you can add some functionality. Let me know if I did anything completely wrong. Maybe maybe there's a bug in here I didn't realize. Again, this isn't the final version at all. This was just a prototype and see if my IDs worked. The mid-side thing didn't work, and I just never cared enough to finish that before making the full plugin. But that's gonna be it for the JSFX EEL2, I suppose, or JSUSonic walkthrough of this code. Let's go to the JUCE. All right, here we are finally in JUCE in C++. So we have a lot of pages here. It looks a little bit scary, but each of these pages are actually doing very little. Really all that's going on is the audio processor, audio plugin processor here is doing all the algorithmic stuff, the behind the scenes stuff, and then the plugin editor is our UI. And for each of these we have a header file and the C++ file. We really don't need to look at the header file. It's just so you know, this is declaring all of our functions, all of the things we need. The tree state, we're going to talk about this very soon. In the save state, we're going to talk about this as well. We have the constructor, the deconstructor. All of this is basically, it comes with as a boilerplate, except for these values I'm adding here, and then all of our parameters here. We'll have to come back and forth so we can see a little bit more of what these things are, but a lot of them probably look familiar to you. So S rate is going to be the sample rate. You can see I'm calculating the RMS size, the window size, in the exact same method as before. We have a floor because, we have integer values for the indices of our window. We have input gain and out gain. This function here is, okay, it doesn't look familiar, but it's something you've seen before. It's just changing the logarithmic value, the decibel value, into a sample value. And for these, I'm gonna go ahead and this is probably the best place to put it. If you're not familiar, or if you're not comfortable with with pointers in C++, you should be aware in case you have an allergy for them. It's something that you have to get familiar with when you work with JUCE. It's not the most brutal thing, but you do have to be aware and cognizant for a lot of the things you're calling. You're going to get pointers, and you just need to dereference them. So that's what the little star is in front of that, in case you're not familiar with that already. So what these things give you initially is just a pointer, and you'll see it's a raw parameter value. That's just think of the raw parameter value as the actual value that you're looking for from a parameter. And again, every parameter is just anything that we're going to turn into a slider. So I'm going to have it run. It takes a while to pull up today for some reason. It's usually not a thing, but here's my other values I use. I have to keep track of the low and the RMS low and the least recent value. All of the variables I had in the other program in JSFX I have here as well. There's a weird detail I forgot to mention about JSFX. You probably noticed it already, but I didn't have to declare these values. So in JSFX, everything's just assumed to be 0. So if I make a value called RMS halfway down the script and I don't declare it anywhere else or instantiate it with a value, then JSFX just assumes that it's a 0. It starts at 0 until I set a value for it. But here I actually do. This is C++. I actually do have to clarify all of my variables. So if we look at everything here, everything I can click, everything I can change, everything that changes value is a parameter. We have our UI elements for them that we'll get to in a bit, but these are the raw values that are going to be connected to these sliders and buttons and such. I hope that's clear. So again, these are atomic values. There's two different threads because we're using the editor, which is the UI, and the processor in the back end. I feel like that's enough information to just keep walking through. The only thing that's very interesting here, I'm just initializing these values. Here's the minimum, the maximum. If we want to know exactly what these are, it's the ID and the name, but you can always check if we don't. Actually, I didn't need to close it, but if we peek the definition, you can take a look and you can see everything that's declared, that needs to be declared, all of the parameters inside this, the instantiation of a parameter float or a parameter int or a parameter boolean. Boolean is just true false, which is why there's not much to say here. Going to the choice one, this is the most interesting. So where I'm declaring this, I give it a list of the names for each thing, and this isn't going to, as you can see, it doesn't correlate directly to what's seen on the interface. This is the default value, so it starts off on sigmoid or the 0 value, and this is what I'm calling it, style. I didn't really know what to think. It's like the distortion type, distortion to style. That's what I called it. And this function is called very, very, very early on when I create this tree state. So the tree state is, again, it was declared back here in the header file. It needs to exist, and it needs to exist like as soon as possible. So we're calling this as part of the brain construct. My brain's okay. Anyway, but we're calling this immediately, along with creating the low pass filter. This isn't a big detail. We might talk about it later. We might not. But to fill this up, I have to fill it up with a parameter layout. And to fill up the parameter layout, I call this function. And this function creates a parameter layout, fills it with these parameters, and then returns it to create my tree state. I feel like that's fair. The listener is what's actually listening from the listener, any sort of listener. It's keeping track of when the values change. And this is one of the weird like thread things that fortunately JUCE kind of abstracts for us. We don't have to worry too much about it, but this is just one of the necessary steps in creating the tree state and allowing it to listen to the changes being made. And that's the tree state is what kind of connects the processor to the editor in this instance. So prepare to play is a lot like the init section in our JSFX. This is where things are declared before we actually start running the plugin. As soon as the plugin appears on a track, this little block of code is run. So again, I'm just changing the in gain and out gain, setting the threshold, which is all changed. I'm changing the decibel value that you set from the parameter into a sample value, and I'm just storing these things for when I actually need to run the actual code. I saved the sample rate as S rate. I'm creating the RMS list, and I feel like, again, this is pretty much the same. It's just in a different language, but it's the same semantically, I suppose. Trying to see if there's anything else interesting here. You'll see lerp. Let's go ahead and take a peek at that file. So I have the utils file from I made this a long time ago, and the lerp function, the bezier lerp function, the same as what you saw in JSFX. Again, these functions I don't even use, but they're handy to have around. I'm hoping to eventually, like as I make more plugins, hopefully this is just going to be a really long utils file, so I don't have to rewrite a lot of these functions later on. And of course, the utils file is imported from right here, so now it has access to all of the functions without having to fill even more functions method space here in the plugin processor file. So where things are actually happening is this process block here, which is it's actually more like the JSFX process, the block part, than it is the samples part, although we eventually act like it's the same as the samples. So what I mean by that is that we're not getting individual samples here, we're getting a buffer. We're getting a bunch of samples all at once. So I have these two buffer writers in this. What we're gonna do for basically the whole function, everything we wrote before, is just iterating through that buffer of, I actually don't know, it's probably 512 samples. I've never checked. But what I also did is I just changed the name of whatever we're at, like this index, this buffer at whatever index we're at, this individual sample, I just called them sample 0 and sample 1 for the left channel and right channel, which gave me the luxury of just copy pasting a lot of code and then just changing things so it works in C++ because I'm going to do the same functions. The only thing that's different, hopefully all of this looks familiar enough to you, the only thing that's different is where I'm allowing it to change between the linear response and the saturated value as opposed to just changing the drive amount. And that code is written right here. So if it's dynamic and aggressive, which means that, yes, let me go ahead and turn it on. So I have to have the dynamics on and I'm on distortion, which means that I need to change, the range knob is going to change how much drive we have. Then I'm going to change the samples to the saturated values. And of course, if it's not dynamic at all, then the saturated value is just this running through when k equals 1, right, by default. If it is dynamic, then k is some interpolation between the drive amounts, drive and drive plus intensity, based on how close the RMS value is to the threshold. I hope that's familiar from our explanation before. And this is where it's slightly different from the JSFX, as opposed to, just being in a different language. And then we have our output gain knob, which is, again, just a linear transformation. We're multiplying by the output gain. And then we spit out these values. So the left channel data at the index we just went through is now changed to whatever I set sample 1 to be, and sample 0, and then sample 1. Why I have the saturation value here, and again, I could have just put saturation value for these, but I have to save the saturation value because that's going to help me in the UI to update the threshold, which changes color depending on how saturated the signal is. So if it's in inverse or not in inverse, if it's in direct, that's going to slightly change. It's just going to be the opposite, right? I just do 1 minus to make it inverted. If the saturation value is high, then I want to see it very colorful. If the saturation value is low, it's going to be dark, and we're going to get into the details on how that's actually graphically shown in a bit. This again is the low pass filter, which I honestly don't think we're going to talk much about today. And again, this is all part of the filter. That's going to be it, actually, I believe, for the plugin processor, besides talking about, almost forgot, this should update part is a trick that I got from the Audio Programmer channel on YouTube. Like, literally, the Audio Programmer is the name of the channel. And what this value tree property change is, it's not something that I'm actually creating from scratch. This is one of the really cool things about JUCE. They have a bunch of functions just for you to override for when things are changed. This happens with the sliders and a lot of other elements, but this is one of the cool perks of the value tree state, and we can look at that a little bit. So you can see I'm overriding it, and this just happens. This is called, usually does nothing, but this is called whenever the value tree property is changed. And the value tree properties, again, as we talked about before, are the parameters. So whenever any of the parameters that I care about are changed, then should update is true. And this is triggered, so as I'm going through the process block, oh, I notice I should update, and then I change all these values, which probably looks very familiar to you. It's exactly like what we do with the sliders in JSFX. So everything kind of has a parallel, although this isn't the same solution for it, I should say. But that's our concepts for the plugin processor. It's really just what we talked about before. We have some beautiful functions that help us. Here's my get RMS value. We're going to use this for the in the saturation value. It's just getter functions. They're going to be helpful for the UI components. So why don't we move on to that? So here we are in the editor where all the UI stuff is going to be. We're making some of our methods that we're going to use. The timer callback is one that we're going to use to update the threshold component. Some of these updates toggle state. I don't even think I actually used this one, but the ones that you see override are things that are automatically in an editor from JUCE, and then we override them to define exactly how they're going to work. For all these list of things, for every single slider or button we need to initialize, we need to have a slider. Actually, I believe I'm using like namespace JUCE, so the JUCE part isn't necessary, but each of these is the actual visual part, the sliders we need. This is our output meter, which is a custom UI component. We'll get to that later. And we have the rectangle bounds. And for JUCE, there's like rectangles its own type of class, and it allows us to do some really helpful functions we're going to see to divide our UI space evenly and easily and quickly. You'll see every button we have. A text button is just a button that has text on it. So you'll see the options A, B, C, D. And you'll notice, again, this combo box, which is interesting. A combo box in JUCE, what it's referring to is a drop-down menu. But if you take a look at the plugin, you see there's no drop-down menu. So what this is actually going to be is I did a clever workaround. These buttons here are actually working like a combo box. When you have a audio parameter switch where you have different like text options you can switch between, it only allows you to do a combo box. But I use this like radio set of buttons to accomplish the same task. And we'll talk a little bit about how I get around that in a bit. We have the labels, which is literally just the labels you see, like the words, distort, drive, the names for them. We have a label for each thing that I have labeled, and then these attachments are the attachments to the actual tree state. So these pointers, unique pointers, these are the pointers that are attached to, well, as you'd imagine, they're attached to the parameters that are actually changing. So that's what, when I touch the slider, it's attached between the slider and the actual parameter so that the value gets changed as I slide. And it's actually doing a lot of things under the hood that makes this process a lot easier. We have separate attachments between the slider attachments and the button attachments because obviously they work differently. And even though, again, you don't see a combo box on the screen, but these buttons are working as a combo box. So I have to initialize the combo box too so that the value can change here. And then when I change the value there, I change the value in the button attachments, and that actually updates the tree state to what I want it to be. So why don't we take a look at what the actual code is in the C++ file. So I have some handy notes for myself, it seems, and this part's just what JUCE gives you as a reminder. When you add buttons, the style combo here is our combo box, as you saw in the H file, the header file. And I need to add all the items that would be on the list. And I had to remind myself, 0 indicates there's no selection. The numbers, the ID and the index are different things. That gave me a bit of trouble for a while. So just a heads up there if you end up using the same sort of trick. When I set the range, this is the range of values that the slider can be on. And again, I didn't add labels for the actual value it's on. The skew factor is a different thing. So let's say, time to draw. If this one actually goes, or even better, let's say that this one goes from 60 to 600, right? But right now it goes to 1,000. But if I know that most people will only be using this area from 60 to 100, and then afterwards, it doesn't matter if this skips like 20 or 50 at a time, because the precision doesn't matter as we go up. So this skew factor can tell it, well, if it's low, most of the values are going to sit on this end, and if it's high, most of the values are actually going to sit on this end. So it's very quickly moves up to 100 and then slowly moves through 600 if I didn't get that backwards. But that's the concept. Then we have our output meter, and this is just me attaching the output meter's values to the tree state, and we'll look at the output meter separately. We set the size of our whole visual screen here. Something we'll notice when we start splitting this rectangle, if I wanted to make it adjustable, there's things we can do instead. But for now, in this version at least, it's just a set size. It doesn't resize. We have this timer, and the timer is super important specifically for the threshold component, because the threshold component needs to be updating constantly. That's why you'll see when we're playing audio through it, it's bouncing around. We have to update this UI component consistently. So the timer, it's on hertz, which means 10 times a second it's going to update to see where this value should be for the threshold. And we're going to talk about this component last. It's something separate than what you would usually typically have on the screen. It's a custom thing. So we set the style. If it's linear vertical, you'll see the input output sliders here are vertical and they're linear. Then we have rotary sliders, which are these round ones. We change the thumb color, and that's the actual color you see here that glows and lights up. And we'll talk about how those things are displayed, because this is I actually made this design. If you can probably recognize this is a little bit, I hope it looks nice. But we designed the sliders, and these colors can change multiple things on the slider. We'll get to that when we get to that. So we have our text box style, and there's no text box. Usually there's a little square. I might actually I can't remember what the options are for this. So why don't I see if I can peek really fast for, okay, I can set no text box, or I can set text box above. Why don't I change that really quick just so you can see what difference this is making? There's usually a little border around these. So if I'll put text box above, we're gonna see what that looks like. For which one? This is the drive slider, so the big one in the middle. Actually, there we go. So we see the text box for the value at the top, and now we can see that the value is changing. And you'll notice I can go this far and still at 1, 2, 3 is right in the middle, and to 6. So if I change the skew factor more, it would behave notably differently. But that's all you need to know about that, I suppose. And let's change this back to no text box, please. We have setting the thumb color. Again, there's methods inside of my look and feel we'll talk about later that's supposed to do this for me, but I ended up doing it here because things didn't work exactly how I thought they would. The suffix is what you'll notice on the time slider here. It says the number and then the letters afterwards. That's what the suffix is talking about. The radio group is the important part of getting these buttons to work with the combo box, and then all that means is that when one is selected, the others aren't selected. So that's what's making it automatically switch for me. When I click one, the other ones go off. So I set the text for each of these buttons, including this on-off button as well. These aren't text buttons. These are, I forgot what they're called. They're toggle buttons, or I believe so. And that's why they don't have the same behavior in that there's no text in the middle. That's the only difference. But again, they're still part of the overall button class, so they have the same message, the same thing for setting text. If I wanted to, I believe I could set text separately, like outside of the boxes here. But the don't send notification part is telling it not to update the tree state immediately, because what we're actually updating is the combo box. So this information is handled in the methods that take care of the toggling the state, which we're about to come up to. So justification is just making sure that things line up the way I want them to. Things are either centered in the middle or centered at the bottom. We can do all kinds of justifications, but that's that. This is the interesting one. So for the response toggle, actually no, these aren't the interesting ones. These are for the toggle buttons. So this is just letting it know that whenever I click it, it does automatically toggle the state. If for some reason I want to be able to click it and it doesn't toggle the state, there's something else that decides if this needs to change. If it's true or not, then I can click that to false, and then have some other function that works with when the toggles are triggered. And making things work when the buttons are triggered is what we're doing here with this weird lambda function. It's kind of odd. So if the toggle state is true, then I have to do these things depending on which button was clicked. So again, you'll notice the drive button, or let's go to aggressive toggle. Aggressive button is this distort button here. If we turn off dynamics, then when I click it, it shouldn't turn orange, right? So that's what I'm doing with changing it between orange or gray, depending on if the dynamics button is on. And this is, again, the dynamics button. If the dynamics button is on, then we do this, or off, then we do this. Then we do the same thing for this button, because Araya, even if we have dynamics on, the drive button and the range button aren't valid, like they don't actually change anything. And it's the same thing of, I decided to make it slate gray. That's the decision I made. We could do different things with the colors. Again, we have all kinds of choices. For a toggle button, the thing that we're changing here is the tick color ID, or we can change the text ID. In this case, I do both. If I wanted to keep it the text orange, I just don't change the text color ID. And these IDs are, it's not changing the color itself. It's saying, okay, I'm going to look at the text color ID for the toggle button inside my look and feel, and we'll get to the look and feel thing later. And then I'm going to change it to this color. That's just the two parameters here. And remember, response toggle, aggressive toggle, curve slider, these are the actual sliders, the visual components that are on the screen. Now I have to make these lambda functions because, well, for each of these I use this lambda function, and that's just for the dynamics button and the aggressive toggle button. For the ones that work as a combo box, I use a different lambda function. For these lambda functions, these are, I don't know why I called it Araya lambda. This is poorly named, but these lambda functions are for all of the button sliders that are connected to the combo box. You'll notice that I'm changing the color differently for different ones. If it's actually the choice Araya, which is the choice D button, then I need to change the colors to gray or orange, right? So it switches to gray, otherwise it needs to go back to orange. So that's what this is about for the colors on the if else on the choice Araya. What this is doing is, it's the most important part here is calling update toggle state and then changing the colors based on which one it's using. Really, all of this junk is just about changing the colors, which is annoying, but what was necessary. And then update toggle state is what's actually connecting it to our combo box, which is style combo. So when I do update toggle state with combo box, with our combo box here, we have this very short function. There's some extra goofy stuff that isn't necessary. I tried a few things before I got this to work. But what it's doing is it takes the button that you pressed, it sets its toggle state to true. And when it sets one button's toggle state to true, because they're radio buttons, the other ones are turned to false, which is awesome. And what it's also doing is it's changing the combo box to the selected item that's attached to the index here. So the index, you'll see, is the last thing that's called it's part of the input for the Araya function. Each one has their own ID, and then it's sending that ID to this function, and that ID is what's changing the combo box value. Because again, what the plugin processor is looking at, the only thing it actually knows is part of the processor or part of the editor is the combo box, and these buttons are actually strictly visual. When I click the button, it really calls this function, it changes the combo box, which is the thing that's changing the values underneath. In the end, it's turned out to be the best option. And again, this is just an on-click function. The reason we use the lambda function is because the on-click function, actually I think we can look at this. This is something that's in JUCE again. It's one of those awesome things where it's designed for you to overload. And this is, hey, look at this. You can assign a lambda to this callback object to have it called when the button is clicked. So every time these buttons are clicked, it calls this lambda function that does the coloring thing, and most importantly does the update of the toggle state for the combo box. Hopefully that explains the weirdness of there's a combo box you don't see on the screen. but that's what's working underneath. For each of these things, we already made the attachments you saw in the header file, and now we need to actually attach them to the slider. So we have the actual parameter name. I believe this is parameter name. It might be parameter ID. It's parameter name, I believe, that's attached to the drive slider. So now this attachment, again, it's what combines the UI, the slider you see on the UI, with the actual parameter value we need in the plugin processor. And the same thing goes on for all of these. And I just separate them by what type of element they are. So we have our sliders up here, then the combo box, and then the buttons. And again, this is just for me to understand it clearer. There's no reason to do this in a specific order. And this, if audio processor saved state is valid, this is just double checking that like a state exists, that it's not calling this before things have been created. And then I have this switch depending on which one's true. I believe I don't even use, do I get this? Oh, okay. So this is when I did this, because when it first starts off, for some reason it works in the plugin version, but the first time I opened this, you probably noticed sometimes none of the buttons are clicked. That's just, it was to fix that, and it fixed it in the VST3, but when I run the standalone plugin, which is what it boots up with, it's still an issue. I'm a little bit confused about that, and we'll probably come back to fix it later. Add and make visible is literally what you think it is. I need to add this to the overall component that's showing on the screen, and then I need to make it visible, and I do that for each thing here. Each of my buttons, you'll notice I don't do an add and make visible for the combo box, because the combo box doesn't exist, and I don't even give it space on the screen. Speaking of giving it space on the screen, is this part down here. So it looks a little bit scary, like a lot's going on, and well, technically a lot is going on. You'll see a lot of weird math going on, like why am I dividing things, and for my pixel spaces. Let's get to our rectangle, which we declared in our header earlier. The way that the rectangles work is actually very cool. So I have a rectangle. The reduce button is going to take, the reduce function rather, it's going to take that much off of each of the sides. Or if I put bounds.reduce and I put one parameter, then it reduces all the sides by that amount. If I have two values, it does the x by a certain amount and then the y by a certain amount. So this is how I take a certain amount of the screen being used. And I do this, I take out like 1/5 because I want some space on the sides here. That's what the reduced ones do. The set painting is unclipped is actually really important if I have two components, right? And I know the actual space that this one takes up is this. I allot it this much space, and the next component is actually allotted this much space. They overlap, and that will cause problems. But that's perfectly fine if I know, and this is just me being confident and telling the computer or JUCE that it's like, hey, I know these things won't actually overlap. Allow their rectangular allotted space to overlap. If I know they're only going to take up this much space, even though it's allotted this much, I can allow these things to overlap. That's what the unclipped is. And I believe that's happening here. Like this drive knob actually has this much space. But I have to set painting is unclipped so I can put this distort button here. And I do that because I know even when I slide the slider, it's not actually going to cross over. They're never going to clip. The reason I'm doing these bounds.reduce, well, more importantly, the bounds.remove from right, this is, I'm not gonna explain every line. That would take a while. But the idea is we have our rectangle, right? When I do when I set one component, let's say the vertical slider bounds is the whole bounds removed from left. I'm doing 1/14 of the width is now equal to my vertical slider bound here. And what that also does is that my entire bounds right here. So this is bounds, right? Before I had this, bounds was this entire big rectangle. Now that I added this remove from left, I have I suppose this is the slider. I'll put S for the slider bounds, and this is bounds. So I've actually reduced, it's both a void function, like it's actually removing this much from bounds, and it returns a rectangle. So this rectangle that it returns is now vertical slider bounds. So then I can further divide it by saying vertical slider bounds dot remove from right is my area for another slider or whatever I would like. Expanded does the same thing as reduced except the opposite, right? So if I have this square, this rectangle, and I say it's expanded 10, then I'm going to expand it this much on the with x because there's two parameters. If there's one parameter, then I'd be expanding in both the y and the x. Hopefully that makes sense for what these functions are doing. And I'm just taking the big rectangle of my entire bounds, and I'm very methodically dividing them into smaller rectangles and then dividing those smaller rectangles, which is why you keep seeing different sections. There's the distortion section that gets divided into different sections for the choice sigmoid button and the choice area button and so forth. It's the same idea. It's hopefully clear in that explanation. This is one thing. It might have been best if I did a bunch of examples, but this video has probably gone on long enough. That is the concept for all of my parts on the main UI. Here's our timer callback, and this one is what's talking about the threshold component. So obviously you could probably guess this meter I drew here isn't part of like a JUCE slider. There's no component built in for that. What I did is actually very close from a tutorial I saw from Akash Murthy. You should definitely check out his channel, not only if you're interested in doing these like audio plugins, but if you're just interested in DSP in general. That is a fantastic, it's one of my favorite channels on YouTube. Very, very well scripted, very easy and fun to watch through sort of tutorials for DSP stuff. And he did an explanation of how to add meters. I'm basically going along with that. I have my extra component folder. My output meter right here I have the bounds like normal. I set its range. I'm setting a rectangle for the bounds and the path. The path is like the outline. It's basically, it's almost like saying draw a line, except this line has thickness and it has roundness on the corners. So the stroke type, it can be curved. Let's go ahead and take a look at what the other ones are. I think there's like beveled or something like that. Oh, not trying to rename it. We'll take a look at what our other options are as well. So we have curved, metered or beveled. There's descriptions for these. The path is basically just like a really flexible line, and you can like connect these so they make cool patterns. We're not going to go into that because this isn't like a UI explanation. This is the RMS value that's passed back and forth, and I have like set level, set saturation. Some of these methods aren't really necessary, but I decided to split them up into this nice little components. Let's see where that's passed. The timer callback function is called. We're going to set the level and the saturation of our output meter, and then we have to repaint it. And we have to do this consistently so that the colored part that you'll see pop up is going along as the RMS changes. So I can change that value if I want, but then that's way more processing power because it's actually doing a gradient here, and that's a lot of CPU for no reason. So I'm grabbing that level that's set every time the timer is called back. I set the color, thumb color, and then I'm gonna do, I don't even keep it orange, but I should change these things. The JMap function is basically saying I'm gonna give you two pairs of values. So I have these values range -30 and 0. If I'm gonna give you one value that I want to map from this range into this range. That's the best way to explain it. So if this value is -15, it's halfway between -30 and 0. So in this range, it should be 0.5, and that's the value it'll spit out. And then I have to do this scaled x so that this value will be the same as the width that I want for my color bar to fill up. I don't even know how to describe that. But again, I have the full width. This is the range from 0 to the full width. And I'm going to fill it up this much based on how much the level, which is going to be some value between -30 and 6, how much the level fills up between here. So if it's at full 6, it'll give me it'll fill up this full width here. If it's halfway there, it'll fill up half of this width here. Hopefully that makes sense. We have our gradients. We have start, end color. This is just making the color gradient so that it starts, let's say it's white here and then orange here, and then it'll fill in that space as you would expect. I fill the gradient, fill that rectangle. This is the part where I have to grab the value tree state from the processor. We'll connect them. And you'll see here, I make my own attachment inside here. Again, this isn't part of the plugin editor here because, again, the component, I made this component very separate. I have to add it and make it visible. And of course, I have to set its bounds as well. I think, oh yes, and then the slider value change is actually, we add a slider, which is this thumb. And I had to make a custom like description of what this thumb looks like. You'll notice I made it a certain type. I'm trying to see, I don't remember where I did that, but this one, yeah, if slider is bar, this is probably the one I changed to work as a thumb. And the cool thing about look and feel, JUCE comes with several look and feels, and when you want your own styling for the sliders and the buttons, what you usually do is you override, or rather you inherit from one of the look and feels like I do here, and then you just change the parts of the components that you want to be different. So like the buttons, the way the buttons look are the same because I don't redefine anything for how to draw a text button, right? I did change draw tick box and draw button background so I get the colors that I want here. And I can do that also for the sliders. So you'll notice I take, most of this is literally just copy paste from what they usually have, and then I add things until it doesn't look like a typical slider. Actually I'm gonna show you that. If I don't override this, there you go. All right, if I don't override draw slider, I get the default sliders for look and feel 4. Let's go ahead and see what they look like. They look like this. Not the vibe I was going for. So, and they're giving me some weird error on their collision box as well. So, yeah, that's a number of reasons I didn't use the built-in one, and that's also part of the allowed clipping I do in the plugin editor. The bounds for these, if they overlap, you get weird kind of glitchy stuff like that. So it is important if you use that function of, what is it, set painting is unclipped, make sure you actually know for a fact that the painting is unclipped for each of these. And again, we're doing the JMap function so that the threshold, the slider is moving between the threshold values. I thought I had it already open, but that's the same idea as before. Here's our slider attachment, the saturation level. It looks like we're good. I think I've covered everything very vaguely, very quickly. And again, the brightness again was the saturation. The saturation value is determined by this value in the processor here, and saturation, these things are passed over to the editor, and then the editor passes them in the callback to the output meter. So again, saturation is something that's calculated here based on how everything else in the interpolation function, whether it's inverse or not, it's grabbed from the audio processor and then passed to the output meter so that I can draw the meter with the right color or level of saturation. And for our final trick, what we're going to do is work together to implement a simple hard clipper at the end of our process block here, so we can get a little bit of experience using all of the things we've learned, adding a little component, adding a parameter, and putting it into our process block. Something to know is that this hard clipper isn't what's going to be in the actual update. I'm planning on using the Air Windows only clip algorithm, which is open source. I really want to thank, I'll see if I can leave a screenshot of the person in Discord that recommended it to me. I really appreciate that. The clipping algorithm sounds great, and I'm actually really excited to hear what it sounds like in combination with these other things, but for the sake of our example today, we're going to do the simplest thing possible, which is just a hard clip. So let's get on with it. we need to add the parameter because this is something that we can change on and off. This is something that the user will decide, dynamically as they use the plugin. So we need to add this parameter to our value tree state. And to do so, it's going to be a Boolean value. Either we're going to clip or we're not, because it's just a hard clipper. There's no interpolate. There's nothing in between. So we have clip. I'm going to call it clip, and clip with a capital. So that's the ID and name, or name and ID. I keep forgetting which order they come in for this audio parameter, which is a Boolean. Great, we're like halfway there. To grab this parameter whenever we need, I'm just gonna grab, instead of like always asking the parameter tree state, hey, what's this value right now? What's this value right now? What's this value right now? Instead, we're just gonna grab a pointer, so that pointer will always show me, when I look at the pointer, it will always show me what the current value is. And what we did was, for these, in the plugin processor header file, is we attach these atomic floats, and atomic is just to make sure that the value is changing one or the other. We don't have to worry too many. It solves issues with multiple threads. Something that is a little bit weird here is I can't remember exactly how it works, but I remember for these we stay with floats. So you notice dynamic and aggressive even in our original parameters. These are Booleans, but for the atomic pointer, we're going to keep it a float. And for the details of that, I'm actually not 100% sure off the top of my head, but I do know we can treat this the same as the others, and I'm going to use the same undercase we used for the parameter name. Now this exists, and I can grab clip, remembering that it's a pointer, whenever I need in my process block. So let's go ahead and do that in our process block. So what we need to know is that if the user decides to turn on clip, then if the signal goes above 1, it'll flatline at 1. And if the signal goes below -1, then it'll flatline there. Actually, there are some people, I've been explaining like the basic DSP stuff, so I might as well continue, right? We have our waveform, right? What a hard clipper does is that it is very aggressive, as you'd imagine from the name. Any part of the signal that's above this line just gets chopped off. So the resulting line is going to look something like this, right? Everything's the same. Oop, I'm not looking for a line. Draw. So everything looks the same, and then there's just a straight line here and a straight line here. And if it goes below as well, -1, then it's the same thing. It'll be a flat line at the bottoms. So it's not quite a square wave because everything in between is still round or whatever shape it originally was. But anything that passes this threshold is going to get literally just chopped off into a straight line. And you can imagine it does sound pretty harsh, but if it's not continuous, like it's not clipped for a very long time, it does go by quite subtly. So let's go ahead and add that in. What I had to do is I realized C++ doesn't have like a simple sign function, which is I find ironic. Like the EL2, like the super basic, like command prompt looking one does have a sign function. So I just added one here in my utils. So if the value is less than 1, it's a negative value. So I return -1. If it's 0, I return 0. If it's a positive value, I return 1, right? So -1, 1, or 0. And that helps with the logic here, because what I'm going to say right after the output gain, although I could put this before the output, I should put this before. So I'll say if sample 0, we're going to do them separately for each channel, is greater than the sign of sample 0. So if it's positive, if it's greater than 1, or if it's negative, if it's less than -1, right? So, and I should put the absolute value, I suppose. Well, wait, hold up. I need to think. If it's negative, then I'm actually looking at less than, right? Well, yeah, but this is the sign, so it's always going to be the right. I have to double check. So since I'm looking at the sign of it, it's always going to be the same, right? So I don't have to worry about it actually pertaining to the wrong thing. Like, just so you can understand what I'm thinking about here, right? If I have this negative value, right? Negative 1.1 is not greater than -1, right? But since I turn them both into absolute values, it's always looking at 1.1 versus 1 here, right? It's a fair comparison. And I know it's the actual sign of the sample because I'm getting the sign of the sample here. So that's going to work out. If it's greater than the sign, then its own sign, then sample 0 equals sign of sample 0, because it's going to equal 0 or -1. And in the case that it equals 0, I don't have to worry because 0 isn't going to be greater than 0. And if it is, it'll just equal 0 here anyway. So it'll equal sign of sample 0, right? And then we're going to do the same thing for sample 1. We're doing left and right separately. Change all of these to sample 1s. I feel like there's definitely a faster way to do this, but I don't know all of my shortcuts quite yet. Let me double check. Oh, there's one thing. We don't want to do any of this unless clip is true. So if, and I want to grab our value clip, right? But clip right now is a pointer. It's this atomic float pointer. So I just have to dereference it, and I'll get the actual value, the raw parameter value. Or let me go ahead and show the raw parameter value of clip here. So it's going to be true or false, 0 or 1 here. And that's the clipper. We're actually done making it work. But there's one problem. When I show this up, right? This thing exists in my process block. But right now the user can't actually change this value. What we're going to see is just the same as before. And I forgot to change. Oops, I got to change that back in the arrow look and feel. Yay, shortcuts. All right. So now that's going to look right, but we don't have a clip button at all. So what we got to do is we're going to go to our plugin editor, and I'm going to have another button, another toggle button. I'm going to call clip toggle. Okay, now my button exists, but it's not going to exist on the interface right now because I didn't make it visible and I didn't give it any position, right? So what am I going to do about its position? This is where it gets a little bit messy because I have to remember how I divided this. I might skip ahead and give myself a second to reread and decide where I want to put this. So, all right, this looks still really ugly, but at least it's there. You get the idea, and we can go ahead and we might stop and check it out in a second. This video is probably already long enough, but the idea is I set the button text here. The most important thing was remembering to I remember I went over it in the video and then I forget to do it myself, but don't forget, above all, add and make it visible. I gave it some space. What I ended up doing is I took the bounds that were for the time slider, which used to be that whole bottom row. I changed that to another rectangle, and then I took the right side of that rectangle to save for the clip space. So now the time slider doesn't have as much room left to right, which is fine, but the clip button now exists. So what I would do usually is I'd fiddle with this for a lot longer, trying to get in the right spot. Maybe I'd change where I put the names for the input-output slider. Maybe that's not really necessary. I think everybody knows what they are there for, so I don't need to put the labels there, but I digress. We have added a hard clipper to our plugin. Why don't we? Go ahead and check it out. I'll fast forward and we'll give that a look to the button that we're toggling. So let's also add our, I'll call it clip attachment. Now this exists, but it's not connected to anything yet. So in the editor, we'll also find where we connected everything. Let's do this. We have a button attachment, and we're attaching it to the parameter named clip, and it is attached to the button clip toggle. Why is there space? There we go. Cool. Now we can build this version. All right, sorry to skip around, but I did test it, and while it did work, yes, it didn't work the way I wanted it to. It's not the best way to express it. So what I did is I actually changed the clipper, so now the clipper is out after the output gain, so it'll be easy to see that it's like doing the clipping or not. There's something about it I don't like, and I'm gonna go ahead and just show you what it is. And again, this wasn't the clipper I was going to implement anyway, so I won't think too much about it. But as it is, you can see, like, if I turn off clip and play, I have it like outputting really loud. It's a warning, right? You can clearly see it's clipping all the red that's showing up on top. If I turn on clip, now it's flat line at 0, right? So yes, we did implement the clipper, right? And it does toggle on and off. What I don't like is when I print it, Reaper's telling me that's clipping a ton, and I think that might be like true. That doesn't even make any sense. That would be like true peak because I'm doing it it might be true peak now that I think about it in between the samples. But you can see these flat lines when we go to the -1 or +1. So it is clipping. It is working as intended. Not the way I'd like though. Well, it's technically working. It is working accurately. The code is doing what we told it to do. But I would definitely myself mess with this more. Either way, we've accomplished all of our goals today. We talked about how we came up with the concept, what techniques, what things we needed to implement in the code. We implemented them in the code through our prototype, and then gave them a nice UI and functionality, and a little bit more functionality using JUCE. And then we even added our own little clipper here at the end. Sorry, we had to skip around back and forth because I get a little bit picky about everything I add. Either way, I congratulate you for watching this video all the way through, and I hope to see you guys in the next video, hopefully not so long or so technical. Thanks for stopping by. Stay cool, everyone.